All right, so last class period, we did complex numbers. We looked at complex numbers and how to deal with complex numbers, where they come from. And then we looked at quadratic functions. We saw how to find the vertex and the axis of symmetry. And then at the end of last class period, we started talking about the x and y intercepts. The y-intercept, there will always be 1 in a quadratic function, we can find by plugging in 0 for the x value. That's pretty easy to compute. We did that with this example last time. This is kind of where we ended off. If you plug in the 0 for your x value, in this case, you get -5. So 0, -5 would be your y-intercept. On the other hand, if we plugged in 0 for the y value, in order to find our x-intercept, it's a lot more difficult to solve. And that leads us to what we're going to do today, which is solving quadratic equations. There's going to be 4 methods that we're going to look at. Although, again, the last 2 are a little bit redundant. Completing the square and quadratic formula are essentially the same amount of work. Maybe not, but there you go. So factoring, square root property, completing the square, quadratic formula. Those are our 4 different ways of solving a quadratic equation in one variable. So let's do factoring first. If we're trying to solve a quadratic equation in one variable, that variable usually is x, then we're going to force our quadratic equation to have the form ax squared plus bx plus c is equal to 0. So I'm going to get 0 on one side and my quadratic expression on the other. Then we're going to factor that quadratic expression into 2 linear pieces. If I have 2 numbers that multiply to 0, then one of them has to be 0. So what I can do, after I factor the left-hand side into 2 linear pieces, I can set each linear piece equal to 0. And then solve each equation. Let's look at this example. X squared minus x minus 20 is equal to 0. So we want to factor into 2 linear pieces on the left. I already have equal to 0 on the right, so I have the form that I want to begin with. And now I have to factor into 2 linear pieces. These are going to be binomials. And the first terms have to multiply to give me x squared. So really the only option for that is that each binomial has first term of x. And they have to multiply to give me -20. Now there's going to be lots of options that multiply to give me -20. 1 and -20, 2 and -10, 4 and -5, and then we can do 5, -4, 10, -2, 20, -1. I think I got them all there. Sometimes I'll write them all. Sometimes I'll just say, hey, these are the two that work. Okay. So there's lots of options for these two numbers. I can put 1 and -20, 2 and -10, 4 and -5. But the key fact here is because this starts with a coefficient of 1, I just need to pick the pair that add up to a -1 here. So I'm going to pick the 4 and the -5 as my numbers that go in here. Those are the two that multiply to give me -20 and add to give me -1. The reason that we want them to add to give me -1 is because when I multiply that out, x and x is x squared, 4 and -5 is -20. I already knew those things. But I'll get two middle terms. One is a -5x, and the other is a positive 4x. And so I want those middle terms to be such that they add to -1. You okay with that? So that's why I'm choosing that. That's how that works. And so now I can set each piece equal to 0. I can set the x plus 4 equal to 0 and the x minus 5 equal to 0. When I subtract 4 from both sides here, I get x is equal to -4. When I add 5 to both sides here, I get x is equal to a positive 5. And both of those values work. So this quadratic has two solutions. One of them is x equals -4. The other is x equals 5. Any questions about that? Now, obviously, they don't always have to. These quadratic equations, in order to solve them, they don't always have to start equaling 0. We can force them equaling 0. We can also start with coefficients on the w squared or the x squared. In this case, we have our variable as w rather than x. So let's solve this quadratic equation via factor. 2w squared is equal to -8w plus 42. I'm going to try to make this as easy as possible. So the first thing I'm going to do is add 8w to both sides and subtract 42 from both sides. When I do that, so I basically added 8w and subtract 42. So I get 2w squared plus 8w minus 42 is equal to 0. And now I have the one side equal to 0. And I'm ready to go. Now, I really like it when I have a 1 in front of the squared term. In this case, I have a 2 in front of the squared term. But notice that the 8 and the 42 are also divisible by 2. So in this particular case, what I can do is I can divide both sides by 2. And that produces on the left-hand side a quadratic whose leading coefficient is 1. And I like to deal with quadratics whose leading coefficient is 1 if I can. You guys understand leading coefficients, the coefficient in front of the w squared. In our form, we had ax squared plus bx plus c, it's the a. So as long as you have a of 1, very nice, pretty quick to factor. Once you get used to this, you'll know that since we have a leading coefficient of 1, it's going to be w plus or minus a number times w plus or minus a number as the factoring. These two numbers have to multiply to give me negative 21 and add to give me a positive 4. 7 and negative 3 multiply to give me negative 21 and add to give me a positive 4. So this is going to be w plus 7 times w minus 3. And that's equaling 0. By the way, we need 0 on the right because the only number that has this property that when you multiply two numbers and you get this value is 0. Okay. This trick only works with 0. If you multiply two numbers and get 0, then one of those has to be 0. So either the w plus 7 is 0 or the w minus 3 is 0. So w is negative 7 or w is equal to a positive 3. Those are the two answers to this quadratic equation. And by the way, if you wanted to check your answers, you could go back up to your original quadratic equation and plug those into w and see that the sides are the same. So if you go plug those two numbers, plug in the negative 7 for w, plug in the 3 in for w, you would figure out that those two sides are the same. Now, there's other factoring techniques that can deal with, lead coefficients that aren't 1. There's other factoring techniques that you can go into rather than just when the lead coefficient is 1, we need numbers that multiply to our c and add to our b. Does that make sense? You guys know what I mean by multiply to c, add to b? I mean in this. I'm not going to go through a lot of techniques of factoring because, quite frankly, we don't need them all. If you get in a bind, there'll be other techniques that can work if you don't know how to factor, right? Or if you don't immediately see how to factor. So the lead coefficient of 1, though, is such a useful factoring technique that you really shouldn't do without it. Okay. So without going over lots and lots of factoring techniques, what we'll do is we'll move on to solving quadratics in other ways. The next option for solving a quadratic is solving via the square root problem. When we solve via the square root property, this is useful when I can get the equation to look like x minus a number squared is equal to some other number. And if I have this, then I'm going to take the positive and negative square root of r and set that equal to x minus h. So x minus h is going to be equal to the positive square root of r and the negative square root of r. So x minus h could have been square root of r or negative square root of r. And then I just solve each equation. So if I can get my equation to look like this, then I can take positive negative square root of the right-hand side, set that equal to x minus h. Essentially what I'm doing is square rooting both sides, but realizing that the x minus h could be a positive number or a negative number. Just as a side note, I use the letter h there on purpose because think of setting y equals 0 in an expression like this. When we have our vertex form of the equation or our standard form of the equation, if we set y equals 0, you can subtract k and then divide by a and you get square root property form. So I chose h on purpose on that because of the x minus h squared connection to that standard form of a quadratic function. So let's do a couple. We have t plus 3 squared minus 36 set equal to 0. And then so I don't have to go back. The next one I'll do is 3 times the quantity x minus 7 squared set equal to negative 75. All right, for this first equation, what we would do is we would add 36 to both sides, and that would give me t plus 3 squared is equal to 36. Now, there's a couple of different ways people write this next step. I'll show you the more common way. The common way of writing this next step is saying t plus 3 is equal to the positive or the negative square root of 36. That's the more common way. You can also split it up into 2 equations, which is what I'm going to do in just a moment. When I think of the first equation, I'm getting a positive square root of 36. Square root of 36 is 6. So you get t plus 3 is equal to a positive 6. The second equation is a negative 6 on the right-hand side. So it's telling you that if you want t plus 3 squared to be equal to 36, then t plus 3 either has to be a positive 6 or a negative 6. And then we can solve each equation. Now, each one of these is solved by subtracting 3 from both sides. So in order to make this original equation true, t could have been 3, or t could have been -9. That's it. That's the whole thing. Once again, I get two answers. One is going to be such that when I plug in 3 here, I get 3 squared. 3 plus 3 squared, excuse me. So 6 squared minus 36 is equal to 0. That's true. If I plugged in -9, -9 plus 3 is -6. Square that, you get 36. Minus 36, you get 0. So that's true as well. So you can check your answers if you want by plugging them into the original equation. Is that all right? Let's go to this next example. 3 times the quantity x minus 7 squared is equal to -75. So here I would want to divide by that coefficient of 3. Divide both sides by the coefficient of 3. We end up with x minus 7 squared equaling -25. Just like before, what we have is that x minus 7 is going to be equal to the positive or the negative of the square root of -25. Now we know how to take a square root of a negative number. That's what we did last time. So we're getting an imaginary I there. And then the square root of 25, if we're positive 25, would be 5, right? So we'll break that up into the square root of the negative, which is I, and then square root of 25, which is 5. And so this is the same thing as x minus 7 is equal to either the positive or the negative of 5i. So x minus 7 is equal to 5i, or x minus 7 is equal to -5i. Adding 7 to both sides. Gives us 2 complex numbers as our answer. We get x is equal to 7 plus 5i, or x is equal to 7 minus 5i. Now, when you type in your answers into Moodle or something, that's how you type them in. There'll be 2 answer slots. And it'll say, you know, here's one, type them in that way. Sometimes, because the only difference here is the sign in the middle, sometimes people shorthand these 2 answers as one equation where they have 7 plus or minus 5i. Does that make sense? So that's shorthand for both of those solutions. In Moodle, you have to type each one out. And by the way, in Moodle, most of the time, it'll say, write your smaller answer first or your larger answer first. Obviously, if we're in this situation, -9 is smaller than +3. So we just order on the real parts. When we talk about bigger or smaller in the complex numbers, it's a little tricky. So in the if you have complex numbers, order on the real parts first, and then the imaginary parts second. So since these have the same real parts, we'd say we'll put this one as the larger one because that's a positive 5 on the imaginary piece, and that one is the smaller one because it's a negative 5 on the imaginary piece. Okay. Even though technically it's not bigger or smaller in the traditional real number ordering sense. Does that make sense? So order on the real parts first, imaginary parts second, when you type in your answer. It'll say that as well, but just want to put it out there. Any questions about this? By the way, if we were doing factoring, factoring would not have led us to imaginary entities unless we could factor over the imaginary numbers, which I wouldn't think anybody, including myself, is not good at in here, right? Factoring over imaginary numbers. So we wouldn't be able to get these types of answers if we're just allowed factoring. But with this square root property, we can get these answers. We can get complex number answers. We can get imaginary answers. Any questions about that? Pretty straightforward. Good. So that's the technique of using the square root property to solve quadratic equations. Now the next technique is completing the square. Completing the square is just essentially one more, albeit fairly complex step to using the square root property. It says, what if my equation doesn't have a nice x minus something squared in it? Completing the square says, let's force it to have x minus something squared if it doesn't already. And so we rewrite one side of the equation to make it so that it's x minus a number squared. And then the other side of the equation will be some real number. And then we just solve using the square root property. But it's called completing the square because I want to get a perfect square on one side. I want to get that perfect square on one side. Right. Now, completing the square will give us all of the same answers, gives us all of the same solvability as this next technique of solving the quadratic equation. And so I want to give you this next technique as well because it's going to be equivalent. All of the same problems that we could solve by completing the square, we could have also solved by using the quadratic equation. The quadratic equation says if we force our equation to be ax squared plus bx plus c, and then we set the one side equal to 0, the solutions will be x values of opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So opposite of b plus or minus square root of b squared minus 4ac all over 2a. For most people, This one is easier to use than the completing the square. So in class, I tend to use the quadratic equation more than completing the square. Is that right? It's kind of like having two tools that do the same thing. So get really good at using one of them. And I tend to use, most people gravitate towards the quadratic formula because it's very sort of a straight path. If you know your A, B, and C, then you plug them into this formula and just keep simplifying until you're done. So I'm going to take a look at this problem. X squared minus 6x plus 13 set equal to 0. We'll solve this using the quadratic formula. Instead of solve via the quadratic equation, so it's a quadratic formula. Yeah, that's fine. That's fine. It's up there before. And then I'll show you, but you don't have to like do this yourself, what completing the square would have done. All right. So let's use the quadratic formula. X is equal to the opposite of b plus or minus square root b squared minus 4ac all over 2a. I'm sure at one point, maybe in high school, you had to memorize that. Maybe some people had to. I had to memorize that in high school, I remember. In this class, I don't care if you memorize it, but you should have it written down somewhere, okay, for reference. In this case, B is a -6, A is a 1, and our C is 13. So every time in this formula that I see the B, I replace it with a -6. Be careful when you do that because we're going to be taking the opposite of a negative. That's going to give me a positive. And then I'm going to take a negative square. That's also going to give me a positive. So be careful about where you place that negative. So -4 times A times C. A is 1, C is 13. So 4 times 1 times 13, all divided by 2 times A, 2 times 1. So we're going to get a +6 plus or minus something inside the square root. That's what I'll type into my calculator. That's a -16 underneath that square root. And then all of that's going to be divided by 2. We are getting the square root of a negative again, so we're going to get another I. And then 16, square root of 16 is 4. So this is becoming 4i. 6 plus or minus 4i divided by 2. When you divide by 2, you'll get 2 answers. 6 divided by 2 is 3. 4i divided by 2 is 2i. So I end up with 3 plus 2i, plus or minus 2i. And when you write that in Moodle, make sure you write each answer obviously separate. Plus or minus is not an answer. What this is referring to are the two complex numbers, 3 plus 2i and 3 minus 2i. By the way, here we've had two complex, we've had two situations in which we had complex solutions. Did you notice that in the previous example and also in this example, our solutions came in the form of conjugate pairs, complex conjugate pairs? And it has to happen that way when we have complex solutions because it's plus or minus, and this is the only spot you can get a complex value, the I part. So if you did get an I in there, it'd be real part plus or minus something with an I. And the plus and minus force us to have complex conjugate pairs. So if you're getting you start with a quadratic equation with nice integer numbers as your A, B, and C. If your answer is a complex number, then your other answer is going to be the complex conjugate of that. Two answers come in conjugate pairs. If it's complex number, obviously, we saw earlier things like -9 and 3 were conjugate pairs. So real numbers don't have to work that way. But if they are complex with imaginary parts, then we're good. Yeah.
Maybe this is a dumb question, but because it was -6 squared, wouldn't it be -6 times -6? Wouldn't that yield a positive number?
It is. It is. So this is 36, and then we're going to subtract 52. And so that's where we got the -16. So this was a positive 36 minus 52, and that's where we get the -16. So I did that all in one step. Oh, I forgot I was going to say something. Now, let me explain completing the square, although this is not a big tool that we're going to utilize. All right? We can take this exact same equation and use completing the square. Let me leave the answers up there. For completing the square, what you would want is you would want something that looks like x minus h squared on one side. Now, here's the trick. If you want x minus h squared, if you multiply out x minus h times another copy of x minus h, you get x squared minus 2hx plus h squared. You okay with that? A lot of times people will say, I don't want to deal with the negatives, so let's just put a positive in there. So people write it that way too. So if I can get my left-hand side to look like this, then I know I can rewrite it to look like this. That's the whole key for this idea. Now, the x squared term and the x term I'm going to leave alone. But I'm going to subtract 13 from both sides. I want to force x, either plus or minus a numerical value, squared. this numerical value, which I'm going to put in, has to be half of the coefficient of x, whether it's positive or negative. You saw when I had a negative sign or when I have a positive sign. It's going to have to be half of this number because of this 2h. So I would have to take half of -6 and put it in here. If I do that, I'm missing an h squared on the end. If I don't have an h squared, it's not going to equal that. So let's force this to have an h squared there. The h is -3. -3 squared is a +9. So we're going to add 9 to both sides. This is why it's called completing the square. You take half of that number and then you square it. Then you add that square to both sides. Completing the square means I've made my left-hand side equal to a perfect square. That gives me x minus 3 squared is equal to -4. And this is what we utilize with our square root property. Now I know that this x minus 3 could have been either the positive or the negative square root of -4. Square root of negative is I, square root of 4 is 2. So we get x minus 3 is equal to either the positive or the negative version of 2i. Add 3 to both sides. 3 is a real number, 2i is imaginary, so they don't combine. I get x is equal to 3 plus or minus 2i. Notice that's exactly the same thing we got using the quadratic formula. So, quadratic formula. And completing the square gave us the same thing. With completing the square, I have to go through this process, which is not nearly as fun. Most people like that, just plug it in and simplify on the quadratic formula over this process, but you can use either. By the way, if the coefficient on x squared is not 1, then you have to divide it. And you can still do the same process using fractions if we have fractions. If you had a fraction here, still divided by 2, you can square a fraction. It's just not as nice looking. So you can use completing the square. You can also use quadratic formula. And it'll work on any quadratic equation that you can write this way. Any quadratic equation where you can get ax squared plus bx plus c equal to 0. So go ahead on your own and try to use the quadratic formula. I guess you could complete the square if you'd like, but I would just use quadratic formula on this equation. All right, I'm going to go through this problem. The first step that we have to do is get one side equal to 0. So we have 2x squared minus 5x minus 14 set equal to 0 if I get rid of the 5x and the 14 on the right-hand side. Now I'll use that quadratic formula, opposite of b plus or minus the square root, b squared minus 4ac all over 2a. I probably won't write that down every time, but for right now I will. b is negative 5, so we're getting the opposite of negative 5 plus or minus the square root. This will be negative 5 squared minus 4 times a positive 2 times a negative 14. Be careful about the positive negative stuff. So 2 is positive, 14 is negative. Negative 14. And then we're doing divided by 2 times 2. So I just need to simplify that. Obviously, when I simplify that, I'll use my calculator. I end up getting an x equals 5 plus or minus the square root of 137 divided by 4. Okay. Now, the square root of 137 is an irrational number. The decimal goes on forever, doesn't have a repeating value. So it's not a nice whole number like we've been dealing with. We've been dealing with square roots of 16 or square roots of 25. 137, it is a real number. It's positive underneath the square root, but it's irrational. Decimal goes on forever. So what I would do is I would say this has two solutions. One is 5 plus root 137 all divided by 4, and the other is 5 minus the square root of 137 all divided by 4. A lot of times Moodle may ask you for your answer as a decimal rounded to a couple of decimal places. That's what it's likely going to do. And so that's what you would do. You take 5 minus the square root of 137, divide that by 4. That's the right-hand one. Sorry, I wrote that over here. That is approximately 1.68, negative 1.68. If I round it into 2 decimal places. And the other one, when we take 5 plus square root of 137 over 4, I get about 4.18. Okay. So a lot of times Moodle would have you plug in the decimal versions of those. Again, they're just real numbers, but with decimal expansions that go on forever. And don't have a repeating pattern. Is that right? Pretty straightforward. And then once you see them like this, pretty straightforward, which one's bigger, which one's smaller, right? One's negative, one's positive. Notice the variety of different answers we were getting. This question, we had answers that ended up as irrational numbers. The previous question, I had answers which were complex numbers. When I factored, I ended up with like integer answers. And so you can get lots and lots of different combinations of types of answers. Go ahead and try this one on your own via the quadratic formula. So let's go ahead and do this problem. Anytime I'm going to use the quadratic formula, I want to make sure that I get 0 on one side. And I always put it so that my squared term is first, my variable with the first power is second, and then my constant is the third term on the other side. Okay. And it's just as easy if you have 0 on the right or on the left. It doesn't matter, obviously. But I always put it in descending order, the quadratic in descending order. In this case, b is -3. I always say that one first because that one's the one that comes up first in the formula. So we get opposite of -3 times the square root of -3 squared minus 4. A is 1 and C is -18. So 4 times 1 times -18. All over 2 times A, again, A is 1. So what we have is 3 plus or minus the square root. Well, this is going to be -3 squared, which is 9, plus, minus 4 times 1 times -18. And that becomes an 81. So 3 plus or minus the square root of 81 divided by 2. Note that the square root of 81 is a nice positive integer, 9, right? So the square root of 81 is 9. And so my two values of x are 3 plus 9 divided by 2. And 3 minus 9 over 2. So that would be 12 divided by 2 is 6. That would be -6 divided by 2 is a -3. And there you go. So this quadratic formula worked when my solutions were complex. It worked when my solutions were irrational. And now you can see it works when my solutions are nice integers as well. So the quadratic formula will work regardless of the circumstance you're in. Okay? So whatever circumstance you're in, quadratic formula will work to solve a quadratic equation as long as I can get it to look like this. So you might say, why didn't we just use the quadratic formula to begin with? Well, because the other methods are often quicker. In fact, in this case, I could have very quickly factored this. Because I ended up with these integer answers, I know it's going to be factorable. So I could have said, well, actually, this is going to be x minus 6 times x plus 3. -6 and +3 multiply to give me -18 and add to give me -3. So that's, I would just factor -18 and the ones that work are -6 and +3. And so factoring is a quicker process when it works. Okay. With the complex solutions and the irrational solutions, factoring is not going to work. But when it does work, it's just quicker. And the same thing is true with that square root property. If I have an equation that already has a squared in it, it's going to be a lot quicker to use the square root property than to try to make it into something that looks like this form and then use the quadratic formula. All right. So the advantage of factoring, the advantage of the square root property are in these circumstances when they work, and the advantage is they're a lot quicker in those circumstances where they work well. If factoring doesn't work and square root property doesn't, it's not the nice format for square root property, then I'd probably just turn to the quadratic formula and do it over. That makes sense? And so there's kind of a hierarchy. If you see, if you're trying to solve quadratics, if it has the form of the square root property, I'm going to use that form, right? If it has that x minus something squared, I can easily get it to x minus something squared is equal to a real number. I'll use the square root property. If it can be easily factored, I'll factor it. If it doesn't have a nice square root property form, and if I can't factor it easily, then I'll probably turn right to the quadratic formula and be done. Make sense? Good. Now remember, this was all motivated by finding x-intercepts. And so we're going to do that. We're going to find some x-intercepts, and we might as well find y-intercepts as well, of quadratic functions. Let's say I have the function f of x is equal to x squared minus 6x plus 5. And we're asked to find the x-intercept and the y-intercept. I'll do the y-intercept first. That's the easier one. That's where we plug in x equals 0, and then everything simplifies. So plugging in a 0 for x. Gives me out a value of 5. So the y-intercept is the point 0, 5. And that's it. Remember, you always get one y-intercept. For the x-intercept, we're plugging in 0 for y. So my output is 0. Doesn't matter if the 0 is on the left or the right-hand side of the equal sign. So we get 0 equals x squared minus 6x plus 5. And then this is obviously not in the square root form. So I'd probably start out saying, are there factors of 5 that add up to -6? There are. -1 times -5, multiply to give me 5, and add to give me a -6. So since this is factorable, this is going to be more easily done via factoring than the quadratic form. So you get x minus 1 times x minus 5 is equal to 0. And then I set each of those pieces equal to 0. So either x minus 1 is 0 or x minus 5 is 0. On this one, I'd add 1 to both sides. X equals 1. On this equation, I'd add 5 to both sides. So x is equal to 5. Okay. Oh, shoot. You know what I should have done? I should have circled that. Sorry. So 1 and 5 are the solutions to this equation, but technically it asks me for my x-intercepts. So x-intercepts are the points 1, 0, and 5, 0. By the way, you can check out and check your answers in a couple of different ways. One, you can plug in 1 for x value and see that you end up getting a 0 out for your output. Plug in 5 for your x value and see that you get a 0 for your output as well. So you can check those answers if you want to by just plugging in 1 into the x and then plugging in 5 into the x. Another way you can check your answers is by graphing and seeing, visually seeing, that we have the right x and y intercepts. So if you go to some graphing tool, I'll go to Desmos. You could also use your graphing calculator to do that. And you just graph you should be able to see your x and y intercepts. Your y-intercept there is at 0, 5. And you can see that this parabola crosses the x-axis at 2 points, which are the 2 points that we found, 1, 0, and 5, 0. So the graph aligns with what we got algebraically. Let's do another example. The function f of x is equal to x squared plus 4x plus 7. So if I want to find the y-intercept, I plug in 0 for x. You'll get out a 7, and therefore the y-intercept is 0, 7. Then you go to find the x-intercepts. In this scenario, when you plug in your y value of 0, you get 0 equals x squared plus 4x plus 7. This looks very similar to the previous problem, but this one doesn't factor over integers. Okay. If you look, the only factors of 7 are 1 times 7 or -1 times -7. Neither of those work. So this thing is not going to factor over the integers. And if it doesn't factor over the integers, I essentially just turn straight to my quadratic formula. Opposite of b will be -4. B is a 4 here. Plus or minus the square root of b squared minus 4 times a times c. A and c are 1 and 7 respectively. Divided by 2 times a, so 2 times 1. So here we're getting 4 squared minus 4 times 1 times 7. That's a -12 underneath the square root. Now I'm going to write this out. This is like -1. 12 you can think of as 4 times 3. And I'm writing it that way because when we went through complex numbers, you know how to do square roots and stuff. We're going to do square root of -1, that's an I. Square root of 4, that's a 2. And then there's going to be a square root of 3 left over. So this is going to simplify to -4 plus or minus. We're going to have 2i times the square root of 3, all divided by 2. So when I divide -4 by 2, I get -2 plus or minus 1i times the square root of 3. So those are my two answers. -2 plus I times the square root of 3 and -2 minus I times the square root of 3. Here, square root of 3 is a little over 1. So 1.73 roughly. But that's it. That's the whole thing. By the way, what does this mean? We solve for x. What does this mean for our x-intercepts? I know. We got complex numbers as our answers. Exactly. There's none. This is a situation where this parabola does not cross the x-axis. My only solutions when y was 0 were complex numbers. And that means the parabola does not cross the x-axis, and there are no x-intercepts. It does not cross the x-axis.
So in Moodle, would we put the two equations or would we put?
Yeah, so this is a good good illustration. We'll get there. There's going to be a distinction here that I'm going to go over in just a moment, which will answer your question. So, just to confirm, we graph this and you can see that the parabola is pointing up and it never comes down and touches the x-axis, right? So, in this case, no x-intercepts. And in Moodle, if it asks you for an x-intercept and it said, here's this blank and then comma 0 and you have to write it, you'd write D and E for does not exist or something like that. Or no solution or whatever. Does not exist would be it. If they ask for x-intercepts. Now there's another way you can ask a question like this, and you can ask for the zeros of the function. We'll get into this soon. But the zeros of the function can be complex numbers. So if it asks you for a 0 of the function, that is an x value that you plug in that gives you an output of 0. All right. Real zeros are the same things as x-intercepts. But there are also complex zeros, which are not x-intercepts. You follow? So what we did in our example was we got no x-intercepts because we had two complex numbers as our zeros. Things that we plug in to the function and get zeros. Does that make sense? Go ahead and try this one on your own. This one, hopefully, straightforward. Right over here. Someone contrast this. All right, let's go through this. So y-intercept, you plug in 0 for x, and when you do that, this becomes 25 minus 2, or 23. And so your y-intercept is 0, 23. To find the x-intercept, you'll plug in a 0 for y. And in this case, because we have this form where we have x plus 5 quantity squared minus 2, it's going to be easiest to use the square root property on this one. I would add 2 to both sides. And then I'd take a square root, making sure to take the positive and the negative square root. I'll probably flip sides when I do that, just because I'm used to seeing my variable on the left. So x plus 5 is equal to either the positive or the negative of the square root of 2. Square root of 2 is an irrational number, but it is a real number, right? So it's a real number that is irrational. So I can't really simplify it, but it is something that exists on the real number line. So subtracting 5 from both sides is going to give me 2 answers. One, which is negative 5 plus the square root of 2, and the other, which is negative 5 minus the square root of 2. When you do the addition, that is a real number, which is about negative 3.59. This is a real number, which is about negative 6.41. Okay. Does this have x-intercepts? Yeah, of course, right? It's just irrational number x-intercepts, right? So the x-intercepts, whether you use the rounded version or the exact version, I'm going to write the exact version, but Moodle may ask you for the rounded version. The x-intercepts are negative 5 plus root 2, comma 0, and negative 5 minus root 2, comma 0. By the way, do you notice that these two x values came in sort of irrational conjugate pairs? For the same reason that our complex conjugate pairs had to come in pairs as well. This plus or minus square root thing. In the quadratic formula forces that to happen, as long as your A, B, and C are all integers. Any questions about that? So we've seen in the last 3 examples, first, we saw one example where the x-intercepts had x values which were nice integer numbers. Then we saw this example where we didn't have x-intercepts, because when we solved, we got complex numbers. Now we have an example where we've solved and we have x-intercepts that are irrational values, that have irrational values on my x. And you could have seen this on the graph too, if you would have graphed x plus 5 squared minus 2. Let's go ahead and do that. You would see that where these 2 points cross the x-axis, they're not at nice integer values. Again, I did this, I'm doing this on Desmos because it's a little bit easier to project, but you could have done this just as easily on your graphing calculator too. Make sense? Good. So that's what we want to do with quadratic functions. We've done a lot, both last class and this class. We've solved quadratic equations a number of different ways. We'll be doing that throughout this chapter, not just today. So we're going to use these tools throughout this chapter to find x and y intercepts. And then don't forget how to find the vertex if we have either the standard form or that general form. Okay. General form vertex has x value opposite of b over 2a. And in the standard form, it's just the hk. Okay. So that's it for section 3.2. So we've seen linear functions. Linear functions would look like f of x is equal to mx plus b if I simplified one side. All right, we saw that back. We're dealing with lines, right? Now we've seen quadratic functions. F of x is equal to something times x squared plus bx plus c. Ax squared plus bx plus c. Notice that we had x to the first with linear functions. Now we have x squared with quadratics. Well, we can move up on our exponents and generalize this concept. So let's start out with the idea of a power function. A power function is any function that can be written as a constant times x to a power. Now you'll notice that there's only one term in a power function. And that's very key here. One term in a power function. So we have a constant times x to a power. And that power can be any real number. It could be negative 8. It could be negative 1.3. It could be a positive 6.4. The power could be square root of x, square root of 3, excuse me. Or it could be 1, or it could be 2, or it could be 5. So as long as it's constant times x to a power, and the constant and the powers are any real numbers, that's a power function. a lot of this chapter is going to be dealing with polynomial functions. A polynomial function is one where we have whole number exponents on our x's. So we can write it in the form a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power, all the way down till we get to a sub 1 times x to the first, and then a sub 0 is a constant, where n is a whole number, and all those coefficients are real numbers. We generally force the lead coefficient to be non-zero. And that's a polynomial function. Notice this, the quadratic functions that we were just dealing with, that's quadratic equations. That was a polynomial function, wasn't it? That could have been expanded and rewritten, and it would be a polynomial function. So all of the quadratic functions we are looking at are examples of polynomial functions. All of the linear functions are also examples of polynomial functions. So let's look at a few functions and determine whether the function is a power function, and then determine whether that function is a polynomial function. I'm going to write all of these out. F of x is equal to 6 times x squared. Then we have below it, f of x is equal to 5 times x to the 1.5 power. To the right of that, we have f of x is equal to 4 times the square root of x. And then bottom right, f of x is equal to 5 to the 2x power. There you go. So I want you to think through these. You don't have to write it down in a second, but I want you to take just a minute to look at all those four and decide whether they're power functions, and then decide whether they're polynomial functions. Okay, so power function is written as k times x to a power, where we can add any exponent. So if we have 6 times x to a power of 2, then it is a power function. All right. It's also a polynomial because the exponent is a whole number. Since the exponent is a whole number, 2 is a whole number, then that's also a polynomial. So that one is a power function and a polynomial. Let's look at the one underneath this. It's 5 times x raised to the 1.5 power. Well, that has this form, so it is a power function. So it's a power function. But it is not a polynomial because 1.5 is not a whole number. How about this one? 4 times the square root of x. Is that a power function or not? Yeah, that one is. That one is a power function via the trick that taking a square root of x is the same thing as taking x to the 1/2 power. Does that make sense? So this is the same thing as 4 times x to the 1/2 power. So square roots, cube roots, we can turn those into x to a power. And so this is a power function because of that trick. It is not a polynomial. Because that power is 1/2, and 1/2 is not a whole number. Now this last one, we have our x value in the exponent. So even though we have an exponent, the x value needs to be the base part to be a power function, right? So this is not a power function. And we need to have whole numbers as our exponents. That's not always going to be a whole number for every value of x. So not a polynomial either. So that one is neither a power function nor a polynomial. By the way, we'll see in the next chapter, this is an exponential function. So this is what we call an exponential function. It's neither a power function nor a polynomial. Now, I don't want to give the impression that every polynomial is a power function either. Power functions have to have one single term. Okay. So if you look at this first function, f of x equals 3x to the 4th plus 5x to the 3rd minus 6x squared plus 8, that is a polynomial because on each of the terms, x is being raised to a whole number power. So that first one is a polynomial function. However, it is not a power function because a power function can only have one term. How about that second one? Is that a polynomial or not? No. 8.2. Exactly. 8.2 is not a whole number power. So that is not a polynomial. It's also not a power function because it doesn't have one term. That's two terms. Third one, is that a polynomial? No, we need whole number powers. Negatives are not whole numbers. Negatives are integers, not whole numbers. So we need non-negative integer powers. That's whole numbers. 0, 1, 2, 3, 4, 5. But negatives don't work, so that last one is not a polynomial, but it is a power function. It is coefficient times x to a power, so that is a power function. So you'll notice that sometimes polynomials are power functions. Sometimes we have a function that's a polynomial function, not a power function. Other times we have a function that's a power function, not a polynomial function. And sometimes there's things that are neither. Some language that we're going to be using with polynomial functions. And again, this chapter that we're going through right now is going to be dealing with all kinds of polynomial functions. That's the main push of this chapter. So the main push of this chapter is polynomial functions. And if we have a polynomial function such that we do not have a sub n being 0, so if a sub n is not a 0, excuse me, then we call n the degree of the polynomial. So the highest exponent on x is going to be the degree of the polynomial of any of our x's. And we call the leading coefficient a sub n. So that's the lead coefficient. So if I use those terms about the degree of the polynomial, which I will, and the lead coefficient, you'll know what I'm talking about. Let's just talk through this. If I look at these three polynomials, these are all polynomials. This first one starts out with the highest exponent on x as the 4. So the degree of this one is 4, and it has lead coefficient of 3. Right? This second polynomial has degree of 5, and the lead coefficient is an implied 1. So lead coefficient is 1. So degree is 5, lead coefficient is 1 on that second. On the third one, the degree is 6, lead coefficient is 9. That's pretty straightforward, right? Hopefully. And if we said f of x equals those things, then we'd say, well, the degree of our polynomial function is whatever I just said. And the lead coefficient of our polynomial function is whatever we just said. Okay. Now, we're going to take a look at a couple of graphs of power functions, and then when those power functions have integer exponents, or actually we'll go through whole number exponents. Does that make sense? So let's start out by just graphing power functions. F of x is equal to x raised to some power. If that power happens to be 1, we get a straight line. If that power happens to be 2, we get a parabola. We already knew that. What if that power happened to be 1.5? Then I get this weird shape. Why doesn't it ever go left of the y-axis? Yeah, well, essentially 1.5 power is like a square root of x raised to the third power. Does that make sense? And since we can't have square roots of negative numbers, so 1.5 is 3/2 as a fraction. So since we can't do square roots of negatives, it doesn't give me anything to the left of the y-axis. So it won't take negative x inputs. That makes sense. As we start growing, notice that certain values won't have negative x inputs. At certain times, like when we put p equals 5, we have this sort of shape where we start on the bottom left, move up and to the right. If you have p equals 6, we get kind of a parabolic shape, but it's not quite a parabola. A little flatter around 0, a little steeper as you move away. Same thing with 4, kind of looks like a parabola shape, but flatter around 0, steeper as you move away. If I keep putting in odd whole numbers, like I put in a 3, I'll get this shape where bottom left goes off to negative infinity, upper right goes up to positive infinity. So with 3, with 5, I get that shape. With 7, I get that shape. Again, notice that as you start increasing your p's, it's shooting off faster as you get further away from 0. As you get closer to 0, it's a little bit flatter. So odd whole numbers are giving us that type of a shape. Even whole numbers, other than p of 0. P of 0 is just a flat line. Even whole numbers give me a parabola type shape, but again, as you get higher, you get flatter around 0 and steeper as you get away from 0. Once you get past 1, you grow really fast. 8, 10, et cetera, et cetera. So all of our even powers are giving us those types of shapes. Our odd powers are giving us shooting off towards the bottom left and upper right. Okay. Oh, shit, hit the wrong button. So there's lots of shapes depending on the p's. Sometimes when those values of p are not whole numbers, we can't plug in negatives. But when p is a whole number, if it's an even integer, then we get kind of the parabola shape where both sides are shooting up. And if we have an odd integer, then we get this shape where moving to the left shoots to negative infinity, moving to the right shoots to positive infinity. So positive even integers versus positive odd integers give us these two shapes. Now, the reason I'm focusing on integers that are positive and integers that are even, or integers that are positive and integers which are odd, is because that's what polynomials do. When the power functions overlap with polynomials, then the exponent has to be a whole number. And so if that power function happened to be a polynomial, we're getting one of these two shapes. Okay. Now, those two shapes can be described by their end behavior. End behavior just means as x is growing, what is y shooting off to? What is the graph doing as x gets bigger? Or, if we're moving to the left, what's the graph doing as x gets closer to negative infinity? So moving to the right, we're moving to positive infinity. Moving to the left, we're moving towards negative infinity. You okay with that? And so that's what the notation is going to look like. This end behavior notation says as x goes to infinity. That just means as you're moving to the right on the graph, what's happening to the corresponding y value? What does f of x do? Or as you go to negative infinity, that's as x goes to negative infinity, what is the corresponding y value doing? And going towards infinity or going towards negative infinity is symbolized by just x and then an arrow and then the infinity symbol or the negative infinity symbol. So that arrow just means going towards something. If you go on to calculus, that notation will be used in limits as well, right? Going towards something. So let's look at our function k times x to a power where the power is even. If I have k times x to a power, if the k is positive, then I'm going to get that parabola shape pointing up. All right? Oh, shoot. P. So P even, K is positive. Then I get a parabola shape pointing up. So as x gets bigger, it's shooting off towards positive infinity. And x gets smaller, it's shooting off towards positive infinity. So both sides are going up, in other words. So this is just fancy notation for both sides going up. If the power is even, but I switch the coefficient from a positive number to a negative number, like if I have negative x squared, or negative x to the fourth, or negative x to the sixth, then we're going to get a parabola shape, maybe flatter at 0 and steeper, depending on what it is. And then both sides are shooting down towards negative infinity. Does that make sense? Why? That's one of our transformations. It just flips the graph, right? Changing from coefficient of positive to negative just flips the graph. So instead of both shooting up towards infinity, now both are shooting down towards negative infinity. By the way, a lot of times, if you're trying to do this in your head, or you're trying to do this manually, it's like hard to keep track of going which things are going which way, right? But if you say, oh, it's this shape, it's that kind of parabola shape pointing down, then it's pretty obvious that both your y values are shooting off to negative infinity. Now, if we have positive odd integers for our powers, then we get that shape where we go from lower left to upper right. So as you're moving towards the right, your y values are growing, shooting off towards infinity. As you're moving towards the left, then your y values are going down towards negative infinity. And the exact opposite is true if we're talking about having our coefficient be negative, because then it flips the graph upside down. I'm going to write this on the board real quick. So we get this shape if E is odd and K is positive. Again, we're talking about f of x is equal to K times x to a power. And then we just flip it upside down. If P is odd, but K is negative. Then moving to the left shoots off to infinity. Moving to the right shoots down to negative infinity. Is that right? So anything that looks like K times X to a full number power is essentially going to look like one of these graphs. Although again, this could be steeper or less steep depending on the values of K and P. Questions about that? When you do problems in Moodle, it'll ask you specifically for the end behavior, and there'll be a drop-down menu that says, you know, infinity, negative infinity, stuff like that. Okay. Or if you have to type in infinity, you could do that too. I don't think I have you do that. But let's look at these three examples. We have f, a g, and an h of x. F of x is equal to 3x to the fourth. G of x is equal to x to the fifth. H of x is equal to negative 1/5 times x to the third. Still. Good. All right. So all of those are going to be one of these types of graphs, and we just have to figure out the end behavior. What I like to do is I like to very quickly look at this f of x, let's say, and say, oh yeah, that's an even power with a positive coefficient. So we're going to be roughly getting something that's pointing up as you move left or right. Okay. Again, drawing a little picture may not seem like a big deal, but you're a lot less likely to mess up if you draw a picture. So that means as x goes to infinity, my y value or my f of x is shooting up towards positive infinity. As x moves towards the left, that means as x goes to negative infinity, my graph is also moving up. And we can do the same thing for these other two problems. Let's look at g of x is equal to x to the fifth. That's an odd power and a positive coefficient. So we know what's going to happen. We're going to get this shape. As we move right on this graph, it shoots up. As you move left on this graph, it shoots down. So that means the end behavior is this. As x goes to infinity, my f of x goes to infinity. As x goes to negative infinity, my f of x goes to negative infinity. H of x has odd power and negative coefficient. So it's going to do something like this. As you move towards the left, shoots up. And as you move towards the right, shoots down. That's what the end behavior is really telling us. We're using fancy notation and infinity and negative infinity. All we're doing is saying, is it shooting up or shooting down as you move left or right? So as you move towards the right, my y values are moving down. So as x goes to infinity, the f of x values are going to negative infinity. X moves to the right, y moves down. As x moves towards the left on this one, my y values are moving up. So as x goes to negative infinity, f of x is going to positive infinity. Left and up. Does that make sense as far as end behavior goes? Again, it's fancy notation, but it's just saying as you move left or right, is it moving up or down? That's the idea. And by left or right, we mean as you move far out to the left or far out to the right. Okay, not necessarily in between. Now, here's the interesting thing. We talked about the end behavior of power functions whose power was a whole number, either even or odd. Well, it turns out the end behavior of polynomial functions are going to be the exact same way as the end behavior of the leading term of the polynomial function. So the term with highest degree or highest exponent is going to determine the end behavior of the polynomial function. Okay. Now there might be some weird things happen in the middle. I don't want to. So when we talk about, or when we graphed these earlier, we just had the parabola shape or this shape where you start lower left and go upper right. Those are our sort of two base shapes. When we have polynomials, you can have other things happen in the middle, but the end behavior is going to be determined by the leading term, that a sub n x to the n. Why is that, by the way? Anybody? Well, the short of the story is this. If I have x to the fourth and I'm comparing it to x to the third, which grows bigger as x gets bigger? X to the fourth grows a lot bigger. If I have x to the seventh and x to the fourth, x to the seventh is going to grow a lot faster as x gets bigger, obviously. And that's going to work for any comparative exponents. We had x to the ninth versus x to the eighth. The x to the ninth is going to grow. And the way I think of it is that this lead term is going to grow faster than all the other terms. And so it's going to dominate the polynomial at the ends. Weird things are going to happen in the middle. But at the ends, that lead term dominates the polynomial. And so it is deciding what it's going to do. The analogy that I always use, I don't know, this is an analogy from a different source, but it's like an elephant and a mouse cross a bridge, and then at the end of the bridge, the joke is the mouse looks at the elephant and it says, "We really shook that thing, didn't we?" They're like, yeah, the elephant's doing all the work, right? Or the elephant's doing all the shaking, okay? The lead term is like the elephant. It's the one that's dominating, that's the powerful one, especially when x gets really big. When x starts getting big, that lead term is going to dominate everything else. And so the end behavior is going to be based on the lead term. All right. So if we look at a couple of functions, that are polynomial functions, we can talk about the end behavior of these polynomial functions. Let me write these down. I'll do them very quickly. F of x is equal to negative x to the fourth plus 4x to the third minus 2x plus 10. And then g of x is 1/4 x to the 5th plus 3/8 x to the 4th minus 6x to the 3rd plus 18. For the reasons we talked about, what's going to happen is this shape for f is going to look like, there might be some weird stuff in the middle, who knows? But at the end, it's going to point down in both directions because negative x to the 4th points down in both directions. Okay. Again, might be some weird stuff in the middle, but function value is pointing down. The function is pointing down as you move both left and right. The same thing is true with g of x in terms of not the way it's pointing, but that the lead term is going to dominate. Even though the coefficient is 1/4, that lead term still dominates. That's a positive 1/4 and x to the 5th. So we're going to end up with some sort of a shape that looks like this. Again, weird stuff might happen in the middle. But as x moves towards the right, my function goes off to infinity, shoots up. As x moves towards the left, at the end, my function is going to shoot down. So it's going to go to negative infinity. All right. Now, real quick, you can always confirm this by graphing. And if you have good software, graph on your calculator, you'll see that it does the right thing. So I've just graphed the f of x here. Notice that at the end, it's pointing down, okay? But like I said, it does some weird stuff in the middle. See how in the middle it kind of goes up and down? So we get some local minimums, local maximums there. And then if you scroll out far enough, you'd see you get another. But at the end, it's moving down. So we have some wiggles in the middle, but at the end, we can see it's going down in both directions. Okay. And you'd see a very similar thing with g of x too. Some wiggle in the middle, but towards the right, it's going off to infinity. Towards the left, it's going off to negative. That work? All right. Well, don't forget about that 3132 homework. That's due on Friday at 5. So tomorrow at 5. Other than that, I will see you next week. All right. See you then.